Moving charges and magnetic fields. All right, so we'd already talked about a little bit about magnetism, what makes a magnet a magnet. Now we're going to get into especially the relationship between magnetism and electricity and something called the motor effect. So the reason why it's called the motor effect will become obvious in a second. But charged particle traveling through a magnetic field will experience a magnetic force that will deflect its path. Now, this doesn't mean that you've got charges necessarily in a current carrying conductor like we talked about last time with the solenoids and the left-hand rule and stuff like that. But you can have a charge flying through a vacuum like a single electron. Or in this case, we've got a picture of what is called a cathode ray tube. So a cathode ray tube is just a tube with a low pressure gas inside. It's kind of like a fluorescent light. And you've got the cathode on one end and the anode on the other end. The cathode in physics 30 is labeled as the negative side and the anode is the positive side. So what happens is when you have a very, very, very negative electrode and a very, very, very positive electrode, the electrons that are inside the cathode will experience a big potential difference such that eventually they'll be able to jump the gap from the cathode to the anode and fly through this gas. And the gas, what happens, you've got gas at low pressure there, it will fluoresce. The electrons will collide with some of the atoms in the gas molecule and give them energy, and then the atoms then re-release that energy in the form of light. So you can see where the electrons are flying through, and these are called cathode rays. They were named before they really were understood what they were, because they look like it's some kind of light or electromagnetic radiation coming from the cathodes, hence the term cathode ray. But literally what they are is just a beam of electrons. So it's got a picture of a magnet, just a bar magnet held by the cathode ray tube, and it shows that the path of electrons is changed by the presence of the magnet. Okay, so one more hand rule. Left hand rule for deflection. So left hand for negative charges, right hand for positive charges, and you put your hand like this. You make a 90-degree angle between your fingers and your thumb. So the thumb represents the direction of the velocity. So whatever direction the electrons or protons, if it's positive, electrons are going, you point with your thumb. The fingers point in the direction of the external magnetic field, and then the magnetic force on the charge will be in the direction that the palm faces. So that's one's easy to remember because when a force is a push or a pull. So when you push something, you might push with your palm. That makes sense. So here's an example. We've got a picture from your textbook where the magnetic field between these two external magnets, a north pole here and a south pole here, if we were to imagine a sort of a north monopole in this region, it would be repelled by this and attracted to that. So you've got the magnetic field that way, in the direction of the fingers. The electron is moving to the right, kind of right and down, sort of in the direction where the thumb is pointed. And then the palm would be directed towards the bottom of the page. So notice this is a left hand because it is a negatively charged particle. Once again, negative charges, use your left hand. So that would look like this. I don't know how it's going to come across on the webcam, but whatever. According to how I'm looking at the screen, north to south is where my fingers go. My thumb points to the right, and my palm ends up facing down. If I do that same thing with my right hand, where my fingers go towards the north, from the north to the south, and my thumb points to the right, notice my palm faces in the opposite direction. So the positive particle would experience an upward force in that case. Okay, so we'll do a bunch of examples here. So for the first one, right here, we decide, okay, well, we got to use our left hand because it is a negatively charged particle. So I'm going to get a pen here so I can draw. So you got a negatively charged particle, so use your left hand. for the first one, the magnetic field would be away from the north and toward the south. So therefore, we would put our our fingers to the right, and our thumb would have to go into the screen like this, because that is the direction that the electrons are moving, into the screen. So if you have your fingers to the right and your thumb pointed into the screen, then my palm ends up facing up. So the direction of the magnetic force is up in this case. Now, we'll do the next three. So let's do this one over here. Magnetic field is in the same direction. The magnetic field is to the right, away from the north toward the south. We notice we have to use now our right hand because we have a proton. We've got a positive particle, and it's going again into the page. So I would place my hand like that. So my fingers are to the right, and my thumb is into the page or into the screen. My palm my right hand ends up facing towards the bottom of the screen. So the magnetic force on the proton would be towards the bottom of the screen. So what I recommend right now is for you guys to pause the video and try the next two on your own, and come back and kind of check your answers. So pause now. All right, so hopefully you did that and you're back. Probably some of you didn't pause, but whatever, I can't control it. So now for this one right here, we've got a positive particle, so you got to use your right hand. The magnetic field is now in the opposite direction, it's to the left. So my right hand is now, my fingers are pointing to the left, and my thumb is pointing into the screen because that's where we're into the page, into the screen. That's where the alpha particle is going. So my palm ends up facing up towards the top of the screen. So if you said the magnetic force is up, great. Now for the last one, we got to switch back to our left hand. Left hand, once again, thumb is into the screen. I got to get used to my webcam here. The magnetic field is now actually towards the left because away from the north towards the south, so the magnetic field is that way. So thumb into the screen, magnetic field to the left, therefore my palm ends up facing down towards the bottom of the screen. So that's the direction of the magnetic force. Okay, so quite often these diagrams are drawn in 2 dimensions instead of 3, because these 3-dimensional diagrams here are kind of hard to draw, especially if you suck at drawing like I do. So quite often we're going to use the symbol that we learned about last time. A dot represents the magnetic field coming out of the page, and an X represents the magnetic field going into the page. So what I want you guys to do is try this yourself. Pause the video again and see if you can find out the direction of the magnetic force. Pause. Hopefully you actually paused and you're back and you're here to check your answers. So let's see. So first decision we make is which hand we need to use. So this is an alpha particle with a positive charge, so we got to use our right hand. The alpha particle is going towards the top of the page, so that means we're top of the screen, so that means we need to point our thumb towards the top of the screen, and the magnetic field is coming out of the page, so my right hand would have to go like this, where my fingers are now directed out of the page, my thumb is pointed towards the top of the page, and that means my palm ends up being to the right. So the magnetic force here is to the right. For the last one, we switch to our left hand because it's an electron. It's got a negative charge, obviously. And so it's going towards the top of the screen. The magnetic field is now going into the screen or into the page because of the X's. So my thumb towards the top because that's the direction of the velocity. My fingers into the screen because that's the direction of the magnetic field. So my palm ends up facing to the right. And there's your direction of your magnetic field right there. Okay. Now, notice when I have my hand like this, and like this, as a matter of fact, my left and my right hand, there is a necessity between, or a relationship between the directions of the velocity and the magnetic field. Because notice those two directions are perpendicular to each other. They form a 90-degree angle. So if the initial motion of the charged particle is parallel to the magnetic field, weird thing about magnetic fields is then it experiences no force whatsoever. A charged particle only experiences a magnetic force if at least some component of its velocity is perpendicular to the direction of the magnetic field. So velocity, magnetic field, notice that forms a 90-degree angle. If they're parallel to each other, or like I can't bend my thumb like that, but in opposite direction, then there is no magnetic force. So we've seen an example of this type of motion back in physics 20. So if the initial motion of the charged particle is perpendicular to the magnetic field, then you get the charge being deflected in a circle. In this case, the magnetic force acting on the charge can also be described as then a centripetal force. So notice for this diagram here, I'm going to tell you that the magnetic field here is into the page in this region right here. And how did I tell? By using my left-hand rule. So let's say at this position right here, the direction of the magnetic force is towards the center of the circle. Say that's the center right there. So that's the direction I put my palm. It says that according to the green path here, the little arrows, that the direction of the motion here is clockwise. So at this point, I'm going to try and draw this with my mouse. The velocity is, well, that's not bad, down and to the left. And when I do that, notice my fingers end up pointing into the page. If I move down here to the bottom, then it becomes like this, because at this instant, the velocity is to the left. The force is towards the top of the page, and therefore, again, my fingers end up pointing into the page. So notice, no matter if I go around a circle like this, my thumb is always perpendicular to my palm. They form a 90-degree angle. So the force and the velocity are perpendicular to each other. Ugh. There's my limited drawing skills with my mouse, but you get the idea. So the word centripetal and magnetic are adjectives to describe that same force. So we talked about a million different centripetal forces before in physics 20. Like, let's say gravity can be a centripetal force because you've got gravitation pulling satellites towards the Earth. And when they're in orbit, you've got an electric force can be a centripetal force where you've got a positive nucleus and a negative electron orbiting the nucleus in an atom. Friction can be a centripetal force where you've got a car going around a curve. So in this case, now you've got a magnetic force behaving as a centripetal force. So what if it's in between? What if you've got not necessarily exactly perpendicular nor parallel, it's in between perpendicular and parallel? Well, what you'll get is, let's say you've got an angle theta here between the direction of the magnetic field and the direction of the velocity. So the direction of the magnetic field is to the right, the velocity is to the right and towards the top of the page. So our velocity then has two components. One component is parallel to the field. The field is to the right, and this is parallel to it because it's to the right. The other component is perpendicular to the field, because towards the top of the page is perpendicular to that. So it's kind of like, analogy can be made to projectile motion, where you have projectile off a cliff, and the x direction there is no force, whereas the y direction you've got a constant downward force, and that leads a parabolic into a parabola. Well, here we've got the horizontal component of the velocity would experience no magnetic force, but the vertical component of the velocity now experiences a centripetal force. So it moves to the right while moving in a circle, and that results in a spiral or helix pattern. Charged particles from the sun can become trapped in Earth's magnetic field. So we said from before that Earth is a magnetic, or has its own magnetic field. It's basically like a bar magnet. The magnetic field is strongest near the poles and weakest near the equator. And we're fortunate to be, or unfortunate, depends how you look at it, in a rather northern climate. And therefore, we're kind of closer to the North Pole than someone would be like in South America, for example. And therefore, we're able to see these effects. You've got charged particles from the sun get trapped in Earth's magnetic field. They spin around in helical patterns, and when they hit the region of the atmosphere that contains gases, they will excite those gases and cause them to glow, just like in a cathode ray tube. Okay. Now, calculating the magnetic force. There's the formula. Magnetic force in newtons. Q, magnitude of the moving charge, so would stand to reason that the bigger the charge, the bigger is the force it's going to experience. Magnetic field strength is measured or expressed in a unit called teslas, capital T. And the faster the velocity, the greater the force. So the magnitude of the velocity perpendicular to the magnetic field. So normally what we're going to do is we're going to either test the two cases, the extreme cases, whether if it's perpendicular, then that that angle between the velocity and the field would be 90 degrees, and the sine of 90 degrees is 1. So that's the maximum force you've got. If it's parallel, then the sine of 0 degrees, 180, is 0. So that means there is no force. Normally, we're not going to mess around with this angle too much. We're just going to either have it be perpendicular, usually perpendicular, or parallel, and if it's parallel, then the force is 0. Okay, now we've got an example problem here. A hydrogen ion travels vertically upward with a speed of 4.65 times 10 to the 4 meters per second through a 8.7 times 10 to the negative 4 Tesla external magnetic field that is directed to the north. Determine the magnetic force acting on the hydrogen ion. So the actual magnitude is not exactly rocket science. So we've got magnetic force QBB, and it is a hydrogen ion. So a hydrogen ion is a proton, because a hydrogen atom, you think about, it's got an atomic number of 1 proton, 1 electron. You take away the hydrogen, or take away the electron to make an ion, and you just got the proton left. So a charge of 1.60 times 10 to the negative 19 coulombs. It's going at a speed of 4.65 times 10 to the 4 meters per second, and the magnetic field strength 8.70 times 10 to the negative 4 teslas. Okay, when you work that out, you get 6.47 times 10 to the negative 28 newtons. So the magnitude is not necessarily like the hard part. It isn't the hard part. Oh, take it easy. However, the direction is well, not hard. It's not hard, but you got to figure out the direction separately. So we've got a positive particle. So you got to use your right hand. So let's see, your thumb represents the velocity, your fingers represent the direction of the magnetic field, and then your palm is magnetic force. Okay, so your thumb of your right hand, it says a hydrogen ion travels vertically upward, points straight up into the air. So hold it straight up into the air in front of you. The magnetic field is directed north. So what I always like to do is when I'm working out these directions, I imagine that north is right in front of me, that I'm facing north, because that way it's easy to sort of visualize. Like south is behind you, east is to your right, and west is to your left. So if you do that, if you point your hand or your right hand away from you and your thumb straight up in the air, kind of like you're going to shake somebody's hand, but your thumb is at a 90-degree angle for some weird reason, pointing straight up, your palm is facing to your left. And if your palm is facing to your left, that means it's facing west. So that's the direction of the force. So your answer is the magnetic force is 6.47 times 10 to the negative 28 newtons west. Okay, next we've got an alpha particle travels east with a speed of 7.00 times 10 to the 5 meters per second through a 3.50 times 10 to the negative 3 Tesla external magnetic field that is directed to the south. Determine the direction of the initial magnetic force on the alpha particle and its radius of deflection. Okay, so radius of deflection, we recall that the magnetic force acting on the particle is a centripetal force also because it causes it to go in a circle. So we remember from um, physics 20, centripetal force, mass times centripetal acceleration. And we know that centripetal acceleration, v squared over r. So then our centripetal force is m times v squared over r. So we see that one of the v's cancels out, and then you can solve for r, radius of deflection. It would be mv over qb. So it's an alpha particle. The mass of an alpha particle is on your data sheet. So you just look that up. It is 6.65 times 10 to the negative 27 kilograms. Let's see. So V, it's going 7.00 times 10 to the 5 meters per second. And then the charge on an alpha particle has a charge of 2 plus. Alpha particle is a helium nucleus. It's a helium ion. So it's 2 protons and 2 neutrons. So 2 protons, 2 neutrons. The mass is on your data sheet as well. So that is, no, the charge. Mass is on your data sheet. So the charge is double the elementary charge. So 2 times 1.6 times 10 to the negative 19 is 3.2 times 10 to the negative 19. Magnetic field strength, 3.50 times 10 to the negative 3 Teslas. And you end up getting the radius of deflection to be 4.16 meters. Then to figure out the direction of the initial magnetic force on the alpha particle, once again, you got to use your right hand because it's a positive particle. So your thumb represents the velocity, and it says it's traveling east. So that's the direction you're going to point your thumb. Your fingers represent the direction of the external magnetic field, and that is south. your palm ends up being the direction of the magnetic force. Okay, so once again, just remember this in your brain, kind of. So that's north, that's south, that's west, that's east. So you have to point your thumb towards the east. So I'm imagining that I'm facing north always. You don't have to imagine that, but that's just what I do. So my thumb then is pointing to my right towards the east. And then my fingers would actually then be pointing straight at me. So, because if I'm facing north, south is behind me. So my fingers are pointing behind me. My thumb is pointing to my right because my right represents east. Behind me represents south because I'm imagining facing north. So therefore, my palm of my right hand ends up facing vertically down. So that is the direction of that magnetic force. All right, and there we have it. There's the basics of magnetic force on charged particles in a magnetic field. Make sure, especially for this online learning, we don't really have a chance to interact besides in the Q&A. I'd like you guys to make sure you read your textbook first, do the practice problems, and then the check and reflect. So practice problems, page 599 to 600, and then page 601, numbers 2 and 4 to 10. Bye for now.